Okay, so let me welcome you to this 8th lecture on our course in reinforcement learning at ASU. And today we're going to talk about the problem of most likely sequence generation in several contexts. There's an old context relating to inference in HMMs, or Hidden Markov Models. This is an area with a vast range of applications that goes back to the 1960s. There's a related context, inference in Markov chains, but there's also a new context that has to do with n-grams and transformers, and then it arises within this context in essentially the same form as in the past in the context of HMMs. And what we're going to do is argue that this problem can be solved by dynamic programming exactly, in principle, but the solution is computationally intractable. So we're going to use rollout algorithms and other types of reinforcement learning methods for this problem, consistently with the methodology that we have been developing so far. So here's the outline. We'll first discuss this problem of most likely sequence generation in the context of n-grams, and also briefly in HMMs. Then I'm going to discuss the formulation of the exact dynamic programming algorithm and approximate versions for solving the problem. Then we're going to talk about rollout algorithms, discuss the issue of performance improvement, various variations. And then in the second half of the lecture, Yucha will take over and discuss some computational experiments with Markov chains and also with a GPT that he has programmed. So let's go to the problem that we're going to be discussing in the context of n-grams. Remember the n-gram context, whereby we generate a sequence of windows. Each window has n words, and it represents the state of a dynamic system, xk, the kth window. And then we apply a certain control, which is the next word that's going to be added to the front of the current window, and the last word of the current window is going to be dropped out. And in this way, you obtain the next window. So this window differs from this one in the first word, which is the choice that we make here, and the last word, which has been eliminated. Now notice that this is a deterministic system. We made this point before, a deterministic control system. The text window is the state, xk, and the word selection is the control, uk. We would like to consider policies that optimize a certain cost function or reward function. And in this particular context that we're going to discuss here, the reward function is going to come out of probabilities, next word transition probabilities that the n-gram produces. Okay. So the problem is deterministic, state control, and now the cost function or the reward function is obtained by looking at these next word probabilities that are suggestions by the n-gram. So you should think the situation here as in text is in texting, and the program gives you next word suggestions. You can follow the suggestions, or you can choose your own, modify the suggestions, or whatever. That's the kind of situation here. But the problem that we're going to focus is to find the next word selection policy that produces a highly likely sequence of text windows starting from the given initial state, which we can view it as a prompt. And highly likely sequence according to the suggestions of the n-gram. Okay, so we're going to view this as a dynamic programming problem where the optimal policy is to select the most likely sequence of text windows starting from x0 and most likely according to the n-grams probability suggestions. So this is the one that maximizes the probability of the generated sequence of states given the initial state. And because the n-gram gives probabilities that usually have a Markov property, and we're going to assume that the probability of the next text window is given all the previous windows, depends only on just the previous window and not the preceding ones. So we assume this Markov property, and this probability of the sequence given the initial state factors as a product of probabilities. So this follows from this Markov property using the multiplication rule of conditional probability. So we assume this Markov property, and the reward that we want to maximize is the product of these probabilities. Now, why would we want to do that? It's not very clear, but it seems like an interesting problem. And it has an advantage in that it doesn't just look at the next word probabilities, but looks also into the future. So that could be useful in some contexts. Now, how are we going to do this maximization? We can use dynamic programming, but then you're going to say, here we have maximization of a product of rewards. In dynamic programming, we have maximization or minimization of the sum of rewards or costs. However, a product of rewards can be converted, maximization of a product of rewards can be converted into maximization of a sum of the reward logarithms. In other words, if we take the logarithm of this reward function, then we obtain the sum of the logarithms, and maximizing the product is the same as maximizing the sum of the logarithms of the terms. Therefore, we can convert this problem to one that fits the dynamic programming framework. And in this particular lecture, we're not going to even bother to do that. We'll state the dynamic programming directly for this product form of rewards. Now, whether you're looking at products or sums of logarithms, you still have the generic problem of exact dynamic programming, namely intractable computation. And this motivates approximate dynamic programming and reinforcement learning methods of the type that we have been discussing in this course. Okay, let's talk about a closely related problem: maximum likelihood inference in hidden Markov models. Hidden Markov models consist of a Markov chain with states and transitions between states, the states as denoted by x0, x1, and so on. And there are transition probabilities that are known, like p sub xk plus 1 given xk. However, we also have data. We're given the original Markov chain with transition probabilities, but we get extra information, data, for each one of these transitions. And what we want to do is find the most likely sequence conditional on the data that we have received. So we get a certain amount of data for the evolution of this Markov chain, and we want to find the sequence of states that matches best the data, in the sense that it maximizes the likelihood of that sequence. Now, this, after you work this all out, it's the same problem as the one that we had before, except that the transition probabilities are modified to account for the knowledge of the data. And there's an additional term here, the conditional probability of the data given the transition. So instead of transition probabilities, we have these weights here, and we want to find the maximum, the sequence of maximum weight, maximum product of weights. Okay, so this has many applications in speech recognition, where the data is the sequence of phonemes, the audio, and the state transition corresponds to the English words. Language translation, the data is a phrase in some language, English, let's say, and the hidden sequence is that we try to estimate is the corresponding translation into French. Computational linguistics are similar problems. The original application of these hidden Markov models was in electrical engineering, in coding and error correction back in the 60s. There are important applications in bioinformatics, sequences corresponding to data from RNA or genome or whatever. Let me just give a little bit more detail about the language translation example. Given an English sentence, a sequence of English words, this is the data. This is the sequence of English words. It may have 5 words or it may have 15 words, okay? In which case, the Markov chain would be 5 states long or 15 states long. And we want to translate this into a the corresponding French sequence, which is a sequence of transition between candidate French words. These candidate French words are the states. Given the data, we form a collection of French words that could match the data, okay? It could be the entire vocabulary, entire French vocabulary, but we don't want to do that. We want to truncate the number of states that we are going to consider. And then from linguistic, from language records and dictionaries, we can construct this weights here, and we can try to find the sentence in French that matches best the English phrase. Of course, each time we have a new English phrase, it's going to be a new problem, new data, new weights, new problem, and so on. And we can go ahead and translate long pieces of text like that, consisting of many sentences. Now, that's the old way, the classical way of doing language translation. I understand now that people use neural networks, deep neural networks, more effectively. And so this example may be a little dated, but I hope that it conveys the basic idea in HMMs. Okay, so now finding the most likely path of states conditioned on the data can be solved by dynamic programming, a shortest path type algorithm known as the Viterbi algorithm, which was invented in the 60s and is still the workhorse in this HMM area. On the other hand, if you have a large state space, the exact solution by the Viterbi algorithm is intractable, and people have worked on suboptimal shortest path type algorithms for solving this problem when the state space is large. Now, what we are going to do is discuss rollout algorithms for the n-gram case and Markov chain case, but these algorithms fully apply to this context. We just replace the transition probabilities with this data-dependent and time-dependent weights that are modified by the data. So that's all I'm going to say about HMMs. It's a vast field. It awaits some further exploration in the context of rollout. It's recent work. It goes. I did this work about a year ago with Yu Chao, and some of you may be interested to explore it further. But that's all I'm going to say today about it. So now let's discuss dynamic programming for this problem of likely sequence generation, focusing on the case of n-grams. We mentioned that the exact solution by dynamic programming is intractable, so we may consider suboptimal policies. And one possibility is the greedy selection policy. We choose the next word that maximizes the next word transition probability. So we look at all the transition probabilities here of the next words and choose the one that has maximum probability. That's what a lot of these next word prediction programs are in texting, that you use in texting. That's what they use. They use a greedy policy. So that's one possibility that generalizes. And we can also use a rollout policy that uses the greedy policy as a base policy. So how does that work? Here we maximize the next word transition probability. Here we maximize the next word Q factor. The Q factor, given that we are at xk, the Q factor for next word being xk plus 1 is given by this expression, is the probability that the next word is going to be xk plus 1, and also the next states are going to be selected using the greedy policy. So maximize the first next word, assuming that the following words are going to be chosen by the greedy policy. That's the greedy Q factor of next state xk plus 1 at state xk. Now, there are a number of variants of this that we have discussed. We can use multi-step look ahead. We can use truncation, where instead of looking at the entire sequence to the end, to stay to time n, we truncate the sequence after a number of steps. Simplified rollout, where instead of looking at all possible next words, we look only at a subset that looks more promising, more likely. And also combinations of simplified rollout, multi-step look ahead, truncated, and so on. Another possibility that we're going to discuss in this lecture is double rollout, which we haven't considered in the past, which is rollout using as base policy the rollout based on greedy policy. In other words, it's rollout on rollout. The base policy of the rollout is the rollout of the first rollout. And you can do triple rollout, quadruple rollout, and so on, except that each time you go to more stages of rollout, there's a computational penalty to be paid, and we'll get back to that. But we're going to talk about double rollout, which is feasible in this problem because the system is deterministic. So you don't have to do Monte Carlo simulation. That would be very onerous in the context of rollout. So that's what I'm saying here. Recall that this is a deterministic dynamic programming problem. And as a result, we can contemplate powerful and sophisticated variants of rollout involving multi-step look ahead, pruning, incremental rollout, a number of algorithms that we have discussed in lecture 6, and also they are further discussed in section 2.4 of your textbook. All of this is possible because the problem is deterministic. So let's give an example, a very, very simple example involving a 1 gram, okay? So the text window is just one word and a vocabulary of just 2 words. So the text window is just 0 or 1, okay? And there are only 2 possible states. Of course, this is entirely trivial, but it's just for the purpose of illustration. N-grams involving natural language have vocabularies of the order of 50,000 words, okay? So it's much bigger. Okay, so this is the problem. And the next word probabilities of the n-gram are as shown here. If you have a 1, then the next word is going to be, the next window is going to be 0. Next state is going to be 0. If you are at 0, there's probability p to go to 0, or probability 1 minus p to go to 1. So what is the greedy policy? Assuming that p is greater than 1/2, if you are here, the greedy policy chooses the most most likely next word, which is 0, right? So the greedy selection policy starting from here, goes here, and then goes here, and goes here, and produces a sequence of zeros. Now, the optimal policy, the most likely sequence selection policy, can be calculated in this simple example. Okay, notice that every 2 steps you're going to end up at state 0, right? So the optimal policy is either going to be like this or it's going to be like this. And we have to compare these two, assuming that p squared is less than 1 minus p. In other words, getting from 0 to 0 along this path, which is the probability is p squared. This is a smaller probability than going from 0 to 1, which is 1 minus p times 1. Then it's clear that the best policy is this one. Not this one, but rather this one. So but not always, if p squared is less than 1 minus p, then this is more likely than this one. On the other hand, if you have the opposite inequality here, the optimal policy is a sequence of zeros. Now, how does rollout work here? Suppose that we are at this state 0. We compare 2 Q factors, the Q factor of this next word and the Q factor of this next word, with the remainder of the sequence computed according to the greedy policy. So what is this Q factor? It has probability P times P times P, okay? And this Q factor is 1 minus P, and then going to 0, and then using the greedy policy, which has P at each step, P probability at each step. So assuming that this holds, the best Q factor is this one, because these transitions are better than these transitions. And you see that the rollout policy is identical to the most likely selection policy. In other words, rollout finds the optimal here, whereas greedy does not in the case where p is greater than 1/2. So greedy looking 1 step ahead, rollout looking at all possible next words, and then applying the greedy, comparing the two, and find the one that has best Q factor and choose that as the next state, and then go to the next state and repeat. Okay, so everything applies, also generalizes to a problem with more states. On the other hand, the state space can be enormous, and an n-gram with vocabulary consisting of Q words involves Q to the n states. And in the case of the English language, Q is like 50,000. So it's an enormous number. It's out of the question to find an optimal policy, but certainly you can implement a greedy policy. And with some shortcuts and ingenuity, the rollout also is feasible. So now let's get into the details of a dynamic programming formulation for the case of Markov chains, where you have transition probabilities from one state to the next. And in this diagram here, I'm showing time on the horizontal, starting at time k, k plus 1, k plus 2, and so on. And on the vertical, we have the state. And trajectories are like this, right? A sequence of states over time. So this defines a deterministic system, but what is a policy? A selection policy is a sequence of stage policies, mu, which given the current state, xk, determines the next state, xk plus 1, according to this function here. And let us denote future states by y. Yik of x and t is the state at some future time I greater than k, starting at state x and using p. So these are the future states when the starting state is x and we have a certain policy. And they're denoted here in this graph. It's the current state, the next state one step ahead, the next state again, and so on, under policy pi. And the probability of such a sequence is the product of the corresponding probabilities. The probability corresponding to the next state transition given x and given the policy p, and so on. So what is the optimal policy here? How can we obtain it? Let's denote it by pi star. It maximizes overall policies, the probability of the remaining sequence starting from x and using pi. So we maximize this expression here and find pi star as the one that maximizes here. It's the optimal policy, and we denote the result as the pk star. The pk stars are like the jk stars of dynamic programming, okay? Star denotes optimal, and the object of dynamic programming is to determine these expressions. They are the optimal reward to go, the optimal reward of the tail problem that starts at time k and at state x. And how does the dynamic programming algorithm look like? Okay, I'm going to state it in a multiplicative form. It starts at the end with a reward to go probability equal to 1. At the end, probability is 1. And then going backwards, we maximize with the probability of the current stage and maximize overall next states. So this is a probability of the next state y, and then the optimal probability starting from y all the way to the end. And so we go backwards, one step before the end, two steps before the end, and so on. And once we reach stage 0, we have the optimal probabilities to go. And after we have those, then we go forward and generate the next words, generate the optimal sequence by maximizing in this dynamic programming expression. The only difference with dynamic programming, the way we know it, is that we had an additive expression, whereas here we have a multiplicative expression. But the same ideas apply because the multiplication involves positive quantities, right? So everything works through. So I could write this in terms of logarithms and then go back to products and so on, but I'm not going to do that. This is the dynamic programming algorithm for the multiplicative form in the multiplicative type of reward. That's what I'm saying here. After we take logarithms of the multiplicative expressions, the cost expression and these expressions here, then we have the usual dynamic programming algorithm in terms of logarithms, and then we can convert it back to the multiplicative form. Now, be it multiplicative or being additive is still a very, very hard algorithm, right? Because this has to be done for all stages or for all states. The greedy policy, on the other hand, which I denote by bar, mu bar, produces the next state by maximization of the corresponding transition probabilities over all y. So given that we are at state x, we look at all possible next states, consider the corresponding transition probabilities, and find the one that has maximum probability. That's the greedy policy. And Okay, a footnote here, if there are ties in this maximization, we want to break them according to a fixed rule in order to have sequential consistency, given that we're going to use this greedy policy for rollout later. Okay, so this is optimal, this is greedy, and let's look at rollout. You've seen this figure before. In rollout, we consider a sequence of states. At the current state, we consider all possible next states. This problem is deterministic, remember? So these next states correspond to the controls that we apply. And then we run the greedy algorithm from here to the end. We do this for every possible next state, and we compare the probabilities of these branches. Compare the probability of this branch, the probability of this branch, probability of this branch, according to transition probabilities of the Markov chain. These probabilities of the branches are the Q factors of the branches. We select the next word that has maximum Q factor, and that's our next word. Then we go on and do the same thing and generate stage by stage the sequence by rollout. It's pretty much like we have seen it before, except that the Q factors are multiplicative rather than additive. This figure shows two-step look ahead. It's possible to do two-step look ahead. We can also do a truncated rollout, where instead of looking at this greedy algorithm all the way to the end, we truncate the greedy selections up to after a certain point. Simplified variants are important. In simplifying a simplified variant, we don't look at all possible next states, but also a subset selected according to some criterion that judges them as most promising. This is very important when the number of next states is humongous, right? Like 50,000. We don't want to compute 50,000 Q factors. We want to compute only a subset of Q factors, maybe 5, maybe 10, but not many. So we have optimal, infeasible, greedy, simple, and rollout based on greedy, which is tractable. Now, this rollout algorithm has a performance improvement property, like the cost improvement property that we have seen in the past. And here's a proof of that. I'm going to repeat essentially the proof of the additive case. Note that we have sequential consistency here because the base heuristic is a greedy heuristic. It's a policy. And policies have the sequential consistency property. They will stay with us after they select a certain greedy trajectory. When they advance along that trajectory, then they will stick to that trajectory and they will not deviate. That's sequential consistency, and clearly the greedy policy has that property, assuming also this rule for breaking ties that I mentioned a couple of slides earlier. Now, what we want to show is that the rollout policy has better performance, better sequence with a better sequence in terms of probability of likelihood than the greedy policy. So that's what I want to show for all x and all k. And I can show this by induction. For k equals n, both for the rollout policy and the greedy policy, these probabilities are equal to 1. This is a starting point of the dynamic programming algorithm. Assuming that this performance improvement property holds for all x at time k plus 1, we're going to show that it holds at time k. And that's basically a one-equation proof with multiple components. Okay, we want to show that this is bigger than that. And we show it by a string of inequalities. Here, the first one is an equality. Pi tilde is a rollout policy. And by definition, it satisfies this expression. It's the probability of the next word selection using the rollout policy times the probability of the remaining selections, again using the rollout policy. Now, this is bigger than this expression, which is the probability of next word selection chosen by rollout and the remainder chosen by greedy. And why does this hold? Because this is bigger than that by the induction hypothesis. And we have the next equation, which compares this expression with this expression. When we are doing rollout, we maximize this expression over all possible next states. And the maximum is attained by the rollout selection. Now, if you plug in here the greedy selection, you're going to get something that's smaller. So we have this inequality, and then by the definition of the greedy policy, again, you have this equality again. So it's a little bit hairy, but if you look at the details, it's quite simple. And it follows by the definition and by the induction hypothesis and the construction of the rollout algorithm. And this is basically a repetition of the proof of cost improvement for rollout in the case of additive cost. I just translated this into multiplicative terms. Okay, we're going to see this performance improvement property in action in the computational results that we're going to give later. But let's talk briefly about the possibility of doing multiple rollout iterations. In particular, let's consider policy iteration. Remember that rollout is the first policy iteration, but you can continue with that with a second policy iteration and so on. And all of this works in a loop like this. You have the greedy policy. You evaluate it by calculating the corresponding probabilities, and then you're improving by maximizing the Q factor, and you obtain the Q factors, and then you obtain the rollout policy, and that's single rollout with greedy as the base policy. Now, double rollout is rollout with a single rollout used as base policy. In other words, we do one rollout, replace the greedy policy with the rollout policy that we have obtained, and do a second rollout. That's double rollout. Triple rollout is a rollout with a double rollout policy as base policy. Kth order rollout is rollout with k-1 order rollout as base policy, and is equivalent to k successive iterations of the policy iteration algorithm. Now, each one of those rollouts can be simplified through truncation and also simplification by pruning out some of the actions, some of the next word selections that seem not promising. And you can also introduce multi-step look ahead if you wish. Now, double rollout works as follows. At an any encounter state, we run the single rollout from every next state and select xk plus 1 to maximize the Q factor over y. But that involves a lot of computation. It's rollout on rollout in a loop, and it requires O of Q times N applications of single rollout, where Q, N is the horizon, right? And Q is the number of possible next states after you simplify the number of possible next words. Still, with every round of rollout, there's an amplification factor of the computation that's given by this. And that can be substantial. So we've done experiments with double rollout. I don't know if we tried any experiments with triple rollout, but even with double rollout, it's the amplification factor is significant. Still, we were able to obtain results with double rollout and much better results in terms of performance. Double rollout is 2 Newton steps. A first Newton step, which can be already very good, and a second Newton step, which is really zooms in the optimum very, very effectively. So I would say that after double rollout, triple rollout would probably produce marginal improvements, relatively speaking. There's also a theoretical result here that's generic to policy iteration. With large enough number of policy iterations, we obtain the exactly optimal policy, the most likely sequence, the exact optimum. That's due to the fact that here we have a finite number of states, and we also have a finite number of controls. So this is a genetic property of policy iteration for problems like that. Of course, to obtain the exact optimum would take a lot of policy iterations, and one would not operate on the basis of trying to find the most likely, the exact optimal policy, except as a test in simple problems. Are there any questions here? Yeah, go ahead.
Since these are Newton steps, does the K order rollout also depend on the starting point? Is it if we start outside the convergence?
If you start outside the convergence region, yes. Yeah, Newton's method works very well as long as you are within the region of convergence. If you're outside the region of convergence, then you're out of luck. However, it seems that in these combinatorial problems, and certainly on this particular problem, it doesn't seem to happen with this greedy policy anyway. Perhaps sometimes you can, greedy policy in this setting, it's not a bad policy really. It's not an excellent policy, but it's not a bad policy. But even if you try poor policies, often you get extremely good, they tend to be within the region of convergence. So don't be discouraged if you can't find a reasonable base policy. Try out a crappy policy and maybe things will work out. I've seen it a few times. Any other questions? Okay, so we'll take a break and come back in 15 minutes.
Let's get started with the second half of the lecture. Now we're going to focus on some of the computational results we conducted using the rollout algorithm discussed in the first half. And before getting to all those computational examples, I want to make a few comments about the previous part of the lecture. And as you may notice that in the first half of the lecture, we have focused on the problems with static transition over different stages, which means the transition probability of one state to the next does not change over different stages. And this is not a requirement for our method, the rollout methodology, to be applicable. And it can be generalized to the case where the transition probability can vary over different stages. On the other hand, we have restricted to this class of problem because it's simpler. And more importantly, it's a case for the language models and transformers that we're going to discuss in later part of the lecture. But otherwise, the methodology applies to more generally to problems where the transition probability can vary over different stages. And also it admits variations whereby you have multiple base heuristics and so on. But at this stage, in this lecture, we focus on the base policy, which is the greedy policy. Okay, Now, we're going to start with a small scale problem whereby the exact solution can be computed by using dynamic programming. In particular, we consider n, capital N equal to 100, most likely sequence of set of C of Markov chains involving 100 states as well. And from each state X, there are 5 states Y such that the transition probability is bigger than 0. So conceptually, the whole Markov chain can be represented by this lookup table. Again, because the transition probability is stationary, we can have one lookup table to represent the whole thing. If the transition probability also varies between stages, then you need to have a lookup table for each stage. And for those of you familiar with linear algebra and so on, of course, this is a matrix. So starting from each state, 1, 2, until 100, the X row is the transition probability from X to all the other states. So starting from this row, each item, let's say this one, is the transition probability starting from 1, goes back to 1, and so on. And given that there are only 5 states that have positive probability, you can expect there are only 5 positive numbers and all the others are 0, right? And it is given in a lookup table. Because the number of states are small, that this is possible. In the next example, in the large scale problem, the lookup table representation is not possible. Again, because the state space, the states involved is small, the most likely sequence can be computed via dynamic programming using backward induction starting from Pn star equal to 1, and you go backward 100 stages, and eventually you get the optimal most likely sequence. And given that we can compute the most likely sequence, we can measure how good the rollout policy is over base policy by a concept we call percentage recovery, whereby this item, this number is the most likely, is the most probable sequence starting from all the states and in all sets of Markov chains we considered. And because this number is just too small, right? If you think about 100 states transition, you have each transition is no more than 1, and eventually you have some number which is so small to deal with. Therefore, we use a geometric mean of this 100 states transition, which means the average transition probability over different states and different Markov chain. And this is how it's computed. And this is the average transition probability under the greedy policy. So from here to here, this difference shows how far the base policy is compared with the most likely transition. Similarly, this is the average transition under the rollout policy, and this is the improvement from this rollout one-step or multi-step look ahead from the base policy. And we use this to demonstrate how much improvement we get by using rollout. And those numbers we call average transition probabilities under different policies. Okay, here are the numbers. And the bottom line is the transition probability, the average transition probability under base policy. Because if you plug in the base policy, you have number 0 in the previous formula. And this line is the optimal policy, right? The percentage recovery from when applying the optimal policy. So we want to show how much this gap is recovered by using one-step or multi-step lookahead. And because the problem is deterministic, we can afford using L-step lookahead rather than one-step lookahead because we are considering sequences of controls, not policies. If in the case stochastic problem, then you are considering policies beyond the first step, then it becomes more difficult. Still, however, recall that from each state, there are 5 states, no more than 5 states that have positive transition probability. As a result, if we do one-step lookahead, we consider 5 next states. And if we consider 2 steps lookahead, it's 25. Up to 5 steps lookahead, you're considering more than 3,000. So 5 to the power 5, more than 3,000 states, right? More than 3,000, yes. More than 3,000 states. So that's a lot of number. But the good thing is with longer lookahead, typically you get improvement. And because there are a lot of simulation to run all the way till the end, we decide to test out how effective it is to do truncations of rollout as well. In particular, this portion is rollout with L-step lookahead. So the subscript is the number of lookahead steps we use. So pi tilde 1 is 1-step lookahead, pi tilde 2 is 2-step lookahead, and so on. And we also run m-step truncated counterparts. So the superscript here, m, represents the number of rollout after which we just truncate the whole thing. Essentially, that means the terminal cost is equal to 0. And this is denoted by pi tilde L, m, where subscript is the number of lookahead and m is the truncation. And as you can see, m is, since we are looking at horizons or sequences 100 steps, right? And we use rollout length is only, simulation length is only 10 steps. So it's 10% of the overall trajectory. But you can see the general observations are rollout lead to substantial improvement over the graded policy in all the cases we tested. Regardless, 1-step lookahead, 2-step lookahead, truncated or not truncated, there are always substantial improvement. And as a general pattern, longer lookahead leads to improvement on average, but not always, as I will show shortly. And this is true in both untruncated rollout, but also the truncated rollout as well. And the performance seems largely unaffected, even though we just truncate, we just use 10 steps of simulation rather than run all the way till the end. So it's only 10% of the whole trajectory we run. But still, it doesn't make big difference in this particular case. So this is the average performance of the methodology. And we will see some particular cases. Yes, please.
Does truncation outperform the version without?
Sorry?
Um,
Yeah, in this case, the truncated version outperformed the untruncated version, right? Theoretically, I cannot see. It's so after you run in the truncation and you use the M stage cost, add them together, and use that as the terminal cost and run the one-step lookahead or 5 steps lookahead. And the rollout theory tells us that the rollout policy is guaranteed to outperform the base policy, but there is no theory really about whether or not the truncation gonna actually bring in benefit. In most cases, it does not, but in this particular case, with longer lookahead steps, it in fact bringing benefit on average, but there is no theory behind it. And typically we find that if you want to run truncation, then somewhere 10, 20 seems to be a good number, especially considering the computational savings. And if you run truncated rollout with m equal to 90, that doesn't save much computational effort. Okay. Yes.
The 10 steps of truncated rollout.
Mhm.
What is the approximation used for that?
0 or 1, you can say. Yeah, it's all the others just multiply with 1. That's equivalent to the additive case you have terminal cost equal to 0. So effectively, no terminal cost approximation. Yeah. Okay. So let's get to some particular patterns of the algorithmic performance. In the previous image, what I show is on average, in terms of average performance characters of the methodology. Now, each figure, the plot here is one particular Markov chain. So the horizontal shows different states. Of course, there are 100 states, so they are indexed by 0, 1, 2, 3 until 99. And different color of the lines show different the cost, the reward under different policy. And the blue one is optimal, and orange one is 1 step look ahead, and 2 steps look ahead, 3 steps look ahead, and so on. And this purple one is the greedy policy. So this one is the greedy policy. And one pattern is shown here, whereby starting from greedy policy with 1 step look ahead, you pretty much get a substantial improvement. But then with 2 steps to look ahead, you get something even better. And 3 steps to look ahead, over all states, you get some improvement in some states. So steadily, with the increase of number of look ahead steps, you get improvement. But you get stuck somewhere, still below the optimal. You get stuck somewhere. But the good thing is, with the increase of number of look ahead steps, your performance is overall improved. Now, this is one case. The second case is here. Starting from greedy policy, running 1 step look ahead is almost already in many states optimal. Then two steps look ahead, some of the states left over picked up performance as well. However, the interesting thing here is if you run 3 steps look ahead, its performance actually in some states, I would say in many of those states, are worse than the 2 steps look ahead. This is one example where the increase of look ahead steps does not bring in improvement. And as we mentioned earlier, this is possible. But I need to stress that we tested many of those examples, and I need to look at all of the data and so on, try to find an example like this. And it's not common, but it's possible. Yes, go ahead. Each plot is the result for one Markov chain. So I randomly generate like 500, I believe, Markov chains. And the Markov chain have different, what we call branching factor. So starting from each state, you have a fixed number of states, no more than that number of states that have positive transition probability. I just randomly generate a lot of those Markov chain. And the result I demonstrated here involving 100 states, and we tested up to 1,000 states with branching factor ranging from 1% to 5%, I believe. And And so each figure here is a different Markov chain. And it's a typical pattern, represents a typical pattern. But this one is less common than the others. But the point I want to stress is that it's possible in some cases, rare cases, you can have longer lookahead steps and the performance actually is worse than fewer lookahead steps. But this is the rare phenomenon. And that's perfectly consistent with the theory, because with longer lookahead steps, what it tells us is you have a performance bound that is better than shorter lookahead steps. But it does not tell you the actual performance, how, for example, your performance bound can be better, but the gap between your actual policy and the performance bound is smaller than the other bound. So it's perfectly possible that this kind of situation can occur. You have a question? Okay. All right. So the other two patterns we have seen, this one is starting from base policy. You have one step lookahead. You have a performance boost. And the second step lookahead is pretty much optimal. And the third step lookahead, you get some further improvement. But even in this case, you can see in some states, like here, longer lookahead step does not bring in improvement. But I need to stress this is the most common situation, and the first plot is the most common situation whereby starting from base policy, one step lookahead get improvement, two steps lookahead steadily get improvement, and third step, again, you get steady improvement. So this is more common situation. Again, let me repeat, each plot is a pattern of a particular Markov chain. So it's not average over multiple Markov chain. And the horizontal represents different states. There are 100 states. And the blue lines are the optimals. And similar pattern are shown in other slightly larger type of problems up to 1,000 states, and with a branching factor ranging from 1% to 5%. Of course, if you have 100 states and branching factor equal to 1, then you have a deterministic problem. There is nothing to study, right? But with 1,000 states, then 1% branching factor is still 10 states. Okay. As I mentioned earlier, because this problem is deterministic, it's possible to run double rollout. And we consider double rollout with one step lookahead and L step lookahead, again with L ranging from 2 to 5. And we denote the lookahead, the exact form of double rollout as pi hat tilde, and their m step truncated counterpart with m equal to 10, again denoted by m hat L superscript m, and the double rollout results are shown here in the blue bars. Remember, this is the number of one step lookahead with not standard rollout, not double rollout. General observation: double rollout algorithm and its variants lead to significant performance improvement over both the greedy policy and the single rollout with one step lookahead. Similarly, the truncated version of double rollout remain effective despite large computational savings. What you can do is, similarly, you can compute the double rollout percentage recovery. You can compute from this figure the percentage recovery of double rollout compared with the base policy, which is a rollout with one step lookahead. And also I need to emphasize that here, our base policy is rollout with one step lookahead, the exact version. There is no truncation involved. The interesting thing you may consider to try is instead of using in the double rollout context, instead of using the one-step look ahead rollout policy as base policy, you may consider using the truncated version of one-step look ahead. And that's going to bring in additional computational savings because since we are using one-step look ahead rollout as base policy, this is mainly the computational bottleneck because we need to run a lot of one-step look ahead rollout. Okay, so in this small scale example, 100, 1,000 states and so on, it's possible to compute the optimal policy. So it's an academic example to demonstrate how much improvement you can get from the rollout. In the next example, we're gonna test the algorithm on GPT, more specifically with GPT-2. And at this point, I believe everyone are fully aware of how powerful the machinery is, the generative pre-trained transformer, abbreviated as GPT. It's a new architecture, like new, it's not really new, many years ago in this era of AI, is improved in important ways on earlier neural networks by using the attention mechanism. I'm gonna talk about that briefly. And such neural networks are often pre-trained with a lot of general purpose data before they are further trained, referred to as fine-tuned in literature, with special purpose data. And owing to both the architecture and pre-training, the resulting neural network are generative, being able to create new content and perform open-ended tasks. And starting from the initial sensation of text generation, nowadays it can generate videos, can generate images and so on, and doing logical reasoning and stuff like that. And it has tremendous amount of application, natural language processing, computer vision, image, and music generation. And in this image is generated by one of those networks. Basically, I put in the prompt to generate something inspiring figure. I don't know how inspiring this figure is, but it showcases how capable all those neural networks are. And we focus on text generation and view the GPT as an n-graph. Okay. The key architecture in the transformer is this attention mechanism, which have demonstrated its potential in tremendous amount of applications and domains. And its key ideas are given as follows. And this kind of illustration applies to what is referred to as decoder-only structure. And in other structures, this representation is slightly different, but we will focus on the one that is applied in this GPT-2. So let us consider this text string. Reinforcement learning is found as an input by GPT-2. It is viewed as 6 words by GPT-2. So we use the GPT-2, and according to its interpretation of words, which is called tokens, this is 6 words. And it's break as follows. So reinforcement learning, the reinforcement is break into 3 tokens. And learning is and found, each one of them is viewed as 1 token. And this special symbol, capital G with a dot on top of it, represents the case where before this learning, there is a space. So this thing is different from the case where there is only learning, because learning will mean that before this token, there is no space. So there are 6 words or tokens. For each feasible ordered word pair, an attention score is generated. And that is represented by this lower triangular of heat map between those words. So the order RE has one score, and yin and RE and yin have another score. And the darker the color is, the higher this attention score is. And it measures the affinity between the ordered word pair. Essentially, it represents how closely related those two, the two tokens are related. And the attention of the neural network is given to the relation with high scores. So basically, the higher, the darker this square is, then more attention it's going to receive from the neural network in the subsequent calculation. Now, how this type of network is trained? Let's again focus on the text string reinforcement learning is fun. In the previous part, recall that if we want to train a neural network to represent a cost function and so on, we need to have the state and cost function pairs. So it's the data, input data, and label, right? But within the text training, within the context of training GPT for text generation, researchers come up with very ingenious ideas to generate the data and label pair, input and label pairs by using this kind of structure. So remember that reinforcement learning is fun. It corresponds to 6 words or 6 tokens. Automatically, that represents 5 training data pairs, input label pairs. So start with the first word or the first token, the first word as input and the second as label. So this is 1 training data. And the first 2 tokens as input and the third token as label. This is the second training data. You can proceed similarly. Then you have, in the end, you have the first 5 tokens as input and the 6th one as label. In total, you have 5 training data, 5 input and label pairs used for training. Using text string to for training does not require explicit data labeling. So because of this automatic generation of input label pairs, it enables the GPT to be trained on the large quantities of text strings. And this automatic generation of labeled data from unlabeled data for training enables the pre-training with large amount of general purpose data. So you give the input to a transformer neural network. The output of this neural network is the probability distribution over the entire vocabulary. Suppose our transformer is focusing on learning this language, and this language is composed of only those 6 words. Then it will be a probability distribution over 6 words. And I will get into this later. But nonetheless, this is output, is the probability distribution. And the label is fitted in the probability distribution, the output of the transformer, and the label are fit together into a training algorithm. Nowadays, people use various off-the-shelf training algorithms quite effectively. And based on the label and the output of the given transformer, the training algorithm modifies the weights of the neural network. And this overall is the training process of the transformer. The label data generation and training process are collectively known as self-supervised learning. It's self-supervised because the text itself generates the supervision, the labels. The training algorithm used for GPT are scaled version of stochastic gradient descent, and we will talk about this in future lecture. Now, if we look at the transformer that we have used, which is GPT-2, we load the weight of the publicly available GPT-2 and then further fine-tune it with an American fiction writer's books. And we get a GPT that hopefully produce something which is more in line with this writer's style. And if you put in as input X0, which is beneath the Asian oaks of the savanna, so this is the input. And this fine-tuned GPT going to generate, as I mentioned earlier, an output, which is the distribution over the entire vocabulary. And for this GPT, the vocabulary size is 50,000. So it's a probability distribution over 50,000. And overwhelming probability in this particular case is G with a dot on top of it. Remember, this is a space. So given that the input is a complete word, it seems it works that it recognizes, okay, there need a space before a next word is generated. But you can see there are other probabilities assigned for other words. And the transition probabilities are generated by transformer. Note that, as I mentioned earlier, for this 100 state Markov chain, the probability is, all the probabilities are stored inside a lookup table with a branching factor that is 2%, 5%, and so on. But when applied algorithm to GPT or large scale transformer, it's not possible to store everything in a lookup table, right? So all the transition probabilities are generated on the fly. And the problem we focus on is n-gram and its associated Markov chain. And the length of the text n-grams, the capital N, the number of states is 200. And the text window is, in the n-gram is 1024. As a result, the number of different n-grams is 50,000 to the power 1,000. So this is the size of state space. And from each one of the state, the number of next state that have positive transition probability is 50,000, right? So the overall state space is all the combinations of vocabularies with the length of text window, which is 50,000 to the power 1,000. And from each one of the states, since the next word is going to be generated, as a result, the number of probability, the number of next state with positive probability is 50,000. So this is the structure whereby our method is well suited. So again, you have a gigantic state space, but the size of the number of states that starting from any states, the number of next state that can be generated with a non-zero probability is relatively small. By relatively small, here is still 50,000, so it's quite large still. The large vocabulary size leads to excessive Q-factor computations. Of course, 50,000 to the power 1,000, you cannot really enumerate it. But even with 50,000, it's a lot of Q-factor calculation. As a result, we applied simplified rollout and its truncated counterparts. So we tested simplified rollout, and also we considered simplification of minimization combined with truncation. But the good news here is both training and inference of GPT typically rely on, or transformers rely on graphical processing unit, GPU, and GPU is highly capable of processing calculations in parallel. And that's well suited for rollout because for the next state, remember, you're going to run the simulation with base policy, which is a greedy policy. And you consider, in the exact case, you consider all next state. And in the simplified case, you consider a few next state. And for each one of them, you run base policy, which is the greedy policy. And this can be run in parallel. Okay, so here is the performance of simplified rollout. We applied two simplification techniques. The first one is computing only 10 Q factors corresponding to top 10, most likely next word. So it's simplified rollout with one step look ahead. Here I have a question. When we apply simplified rollout without truncation, and this, we only consider top 10, only consider 10 Q factors corresponding to top 10 most likely next words. And in this case, I can say with guarantee that the obtained rollout sequence is well outperform the greedy policy, even though I have incorporated a simplification, has proved many of the other next word. I only consider 10 Q factors instead of 50,000, but I can still say with certainty that the rollout generate a sequence that is more likely than base policy, which is a greedy policy. Can you tell me why? Yes.
Most likely it's included in top 10.
Exactly. So this is the thing in the previous lecture we have alluded to, that when you do simplification, typically if you have a base policy, then it's good that the base policy is used in certain way to help you construct the constraint set, or the subset of the constraint set for you to consider, because basically to ensure the performance improvement. And in addition to that, we also introduced the truncation, truncating the simulation after 10 steps. It's M-step truncated rollout. As you can see, the general observation here are simplified rollout has substantial improvement over the greedy policy with modest computation increase. And the truncated counterpart still improves upon the greedy policy in all of our test cases. Let me explain to you this plot. So we have a fine-tuned GPT-2, and we use GPT-4 to generate the initial states. So I give the prompt of GPT-4 that give me an opening sentence for a fiction and things like that. So each data point represents the opening scene or the opening sentence generated by GPT-4, and that's the X0. And I use that X0, feed into this fine-tuned GPT-2, and ask it to generate a subsequent sequence of text with length 100. And so each data point represents a different text generated starting from the different initial sentence. Again, because this is a deterministic problem, we don't need to run simulation multiple times. Everything is deterministic. And you can see in some cases, the exact rollout appear to be important. Doing truncation heavily reduce the probability. And in some cases, truncation does not affect the performance at all. Okay. Any questions here? in the next lecture, okay, even at this point, in this lecture, we have talked about the most likely sequence and for HMM and for Markov chain, but interestingly, it's a deterministic problem. And up until this point, we have focused on deterministic problem in the specialized lectures and methodologies. Starting from next lecture, we're going to focus on stochastic problem and continuous space problems. And those includes rollout and approximation in value space applied to those problems, including Monte Carlo tree search and model predict control. Okay.